Hello Bobcats. In this video we will be discussing thermochemical equations and stoichiometry. So let's discuss what a thermochemical equation looks like. So thermochemical equations. There's two ways to write thermochemical equations. You can include the energy in the equation itself, or you can write the equation and then write the delta H or the enthalpy change of the equation to the side. And let me show you what I mean. So, thermochemical equation. In general, what you can say is that we can say that if we have reactants going to products plus heat, so if we put heat on the product side, that is an exothermic reaction, and we know that delta H will be a negative value, and we can say that's exothermic. Now, if we have reactants plus heat produces product as a thermochemical reaction, the heat is now written on the reactant side, and so the delta H will be a positive value and it will be endothermic. So if heat is written, the heat value is written on the product side, it's an exothermic reaction and delta H is negative. If the heat value is written on the reactant side, delta H is positive and it's endothermic. So for a couple examples, that black pen is running out. Let me grab another black pen. So for example, if we take 2 moles of aluminum solid plus 3/2 moles, and I'll explain why we have a fraction here in just a minute. I know, even though we haven't had fractions before as coefficients. So 2 moles, 3/2 moles produces 1 mole of Al2O3 plus 1776 kilojoules per mole. Okay, so that's energy per mole. And if you'll notice, I wrote this on the product side, so this is an exothermic reaction. And if we are including the value as part of the equation, we don't write the negative sign here. Or we could write it as 2 moles of aluminum plus 3/2 moles of oxygen gas will produce 1 mole of aluminum oxide, that's supposed to be solid, aluminum oxide solid, and then to the side we can say delta H is equal to a negative 1776 kilojoules per mole of reaction. Okay, so you'll notice that I either can include the value as part of the equation, but we don't put the sign. It depends on which side you put it. If it's on the product side, it's exothermic. If it's on the reactant side, it's endothermic. This case is on the product side. I can also write it as just the reaction, and then to the side write the delta H is equal to the negative 1776 kilojoules per mole. Now, and this is understood as per mole of reaction. So this up here, what we have to interpret this is that 1 mole of reaction, based on how it's written here, is said to occur when 2 moles of aluminum reacts with 1.5 moles of oxygen to produce 1 mole of aluminum oxide and 1,776 kilojoules of energy, of heat. Now, so this is written so that it works with these coefficients. Now, let me explain why we have 3 halves here. So if you wrote the reaction, let's look at the reaction originally. So if I have aluminum solid plus oxygen gas to produce aluminum oxide solid, we would balance it so that we would have, let's see, we have 2 aluminums here, 1 aluminum, we have 2 oxygens, 3, so I need to put a 2 here. 2 times 6, 2 times 3 is 6, so I need a 3 here, and then a 4 here. Now that's the original balance, but based on how this is written, we're looking at this 1776 kilojoules per mole of reaction based on 1 mole of product being produced. So I have to therefore go through and divide each of these by 2 so that I get 1 mole here, so that it really ends up written as 2 moles of aluminum plus 3 half moles of oxygen produces 1 mole of aluminum oxide, and then that would be with a delta H value of a negative 176 kilojoules per mole based on how this is written. Okay, and in this case per 1 mole of product produced. Now if I were to write the delta H up here, we would, for the balanced reaction up here without dividing, then I would have to double this, and so double 1776 this would be a negative 3,552 kilojoules per mole based on this reaction before you divide by 2. Okay, but most reactions try to base it on either a mole of product produced or 1 mole of one of the reactants. So in this case, that's why we have the 3 halves, because to get to 1 mole of something here, we divide by 2 to get 1 mole of product. Now, but really, we just need to really pay attention and say that this value is based on these coefficients. This value would be based on the 4, 3, 2 coefficients, okay? And much of the time, and I should say mole per reaction down here, Rxn, mole per reaction here, Rxn, and mole per reaction. So most of the time, this writing it as mole per reaction is not included in the enthalpy value. Because it is understood to be mole of reaction as is written with the coefficients, as it is written. Okay, so a lot of times it'll just say negative 1776 kilojoules instead of kilojoules per mole, but it is understood that it's per mole of reaction based on the coefficients as it is written. Okay, so let's do some practice problems with stoichiometry of thermochemical equations. so thermochemical stoichiometry with thermochemical equations. Boy, can't write it correct, can I? Thermochemical equations. So let's look at the stoichiometry with thermochemical equations. Sorry about the mess there. So let's look at, we're going to do 4 different practice problems here. And the equation that we're going to use, the thermochemical equation that we're going to use, is 1 mole of methane gas plus 2 moles of oxygen gas will produce 1 mole of carbon dioxide gas plus 2 moles of H2O gas, and then we're going to say that the delta H is equal to a negative 891 kilojoules per mole of this reaction. Okay, so that means 891 kilojoules if you burn 1 mole of methane, 891 kilojoules if you use 2 moles of oxygen, and so forth. Okay, so the first problem let's do is let's determine the amount of heat produced by the combustion of 3.30 moles of methane. Okay. So again, if you notice here, as I go through this, I want to know, determine the amount of heat. And so I want to know how many kilojoules of energy, if not, and this is kilojoules of energy per 1 mole of methane, but I'm actually wanting to know 3.30 moles of methane. So I have more methane than just the 1 mole. But we do know that for every 1 mole of methane, based on the coefficient from the reaction, 1 mole of methane will produce this much energy. So that's a negative 891 kilojoules. And so that's all there is to that one, because now I have kilojoules. So that's a 3.3 times 891, and we want 1, 2, 3 sig figs, so my answer is going to be a negative 2,940 kilojoules of energy. Now in this case it's not energy per mole, it's per 3.3 moles. So we don't write per mole here because we're not looking at the whole reaction, we're just looking at these values. And everything, all answers should be in kilojoules from here on out when we're looking at energy, not just joules but kilojoules. The next one we're going to look at is this question, number 2. So determine the amount of heat produced. So we're still looking for heat produced, but in this time, instead of looking at the methane, I want to know how much is produced when 54.0 grams of oxygen gas is reacted. So this is how much oxygen I have to react. So I want to know how much heat I can produce. Okay, so let's look at this one. And again, I'm looking for amount of heat. So I want to question mark kJ, kilojoules. We know how many kilojoules of energy, and now I start with the 54.0 grams of oxygen. Now hopefully by now you realize, and since this is in moles, I know I have to get to a mole. But if I don't have the mole of something, if you have the mass, go to the mole by using the molar mass conversion. So 1 mole of O2 is 32.0 grams O2. Now remember, I put the grams on bottom because they're on top over here. Now I have moles of O2, and I know that for every 2 moles of O2 I produce that much energy. So for every 2 moles of O2 I get a negative 891 kilojoules of energy. And this is fairly straightforward stoichiometry problems. Let's see if it looks kind of weird. I'm going to try to straighten this out a little bit. Okay, hopefully that works a little bit better. Anyway, so when I calculate this, multiply and then divide, I get a negative 752, that's 3 sig figs, kilojoules of energy produced. So by burning this much, 54 grams of oxygen, this is how much energy gets used. Okay, so let's look at another sample. Number 3. Determine the mass. So instead of looking at energy, let's say I wanted to determine the mass of water, H2O gas, produced during an enthalpy change of negative 423 kilojoules. So what this is really saying is, if I have this much energy available, negative 432, or I have this much change in energy, how much oxygen can I produce when this much energy is produced? So again, we start, and I'm looking for grams. So in this case, I'm determining the mass of oxygen when I have the amount of energy. So how many grams of oxygen? I keep saying oxygen, I meant water, sorry. How many grams of water are produced when this much energy is used or produced? Sorry, when this much energy gets produced. So again, we know that this reaction is a negative 891 kilojoules for every 2 moles of water, because we're looking at water. So I'm going to write a negative 891 kilojoules for every 2 moles of H2O. Now I don't want moles of H2O, I want the mass of H2O, so that's going to be 1 mole of H2O. I put it on bottom because it's on top here. It has a mass of 16 plus 2.02 is 18.02 grams of H2O. And when I multiply and divide, I should be able to produce 17.1 grams of water from that much energy change. Okay? So hopefully you understand these are really straightforward. And the last one I want to look at is, what if we double, and I already introduced this, but let's just say, let me use the last one here, black. Number 4, determine enthalpy for the reaction below. determine the enthalpy for the reaction. Instead of just one, we're going to say 2 moles of CH2 plus 4 moles of O2. This is a gas. This is a gas. Produces 2 moles of CO2 gas plus 4 moles of H2O gas. And in this case, all we did is we doubled the coefficients. Remember, this is 1 mole here. This is now 2 moles here. So we just doubled the coefficients. So my delta H for this reaction is equal to 2 times the original value. And we get a negative 1782 kilojoules per mole. Okay. Oops, let me move that up so you can see. Sorry about that. And that's the basically what you need to do for stoichiometry. And we will stop this video here.